Hi, welcome to my channel. Today again I am going to solve some more problems related to the trie data structure, and I'm going to use a website called Leetcode. So let's get into it. Some of my friends suggested to solve some problems from this website. Apparently there are lots of problems related to the different topics, and this website is really good if you are for example preparing for the interviews. So please check it out. Apparently there are some problems related to the trie data structures, and today I'm going to use these first three problems. I checked out the first and the second one is very similar to the one to my previous video, and the third one is it's also interesting. I'm not sure if the trie is required there, but I'm going to try to solve it with the trie. So Leetcode has its own editor, which comes with its own key binding, so it's not Vim editor, so I don't want that. So apparently here you can directly type into here, and then you can also change to the Vim key bindings, but I wasn't very satisfied with this, and I don't get my own Vim settings. So I looked for the plugin, and there was indeed a Vim plugin. So I set it up. It was very smooth. I didn't see any problems. If you follow the documentation, you should be able to use Vim to get the problems and to submit the problems. So today I'm going to do that, and let's we are going to solve the problem number 208, 211 and 212. So let's solve them. First of all, I'm going to sign in to the Leetcode. Okay, I'm signing in. Then let's get the problem list. Okay, now I can directly go to the problem. So here, this is the one we are going to solve, and I can open it, and it also downloads the problem description. So this is a standard trie data structure requirement. So we need to have a method for insert, for search, and for starts with. Basically we insert some words into the trie, then we try to search for the word if it was inserted before, and we are also searching for if there is a word which starts with some prefix. So here again we assume that all the letters are lowercase English letters, and all the inputs are going to be non-empty strings. So basically this is a standard trie implementation, and we can implement that as in my previous video. So let's jump into the implementation. So very first thing I'm going to do is I'm going to create a trie node class, and let's call it node. And if you remember, we had two attributes, and one of them was isWord, but today I'm going to rename it to isEnd, which indicates that this node is a last letter of some word which was inserted. And of course we need children, and let's also initialize when we create this node. So isEnd is going to be false initially, and this children. And today I'm going to use array of size 26. And of course, let's also add our root. And let's also initialize it when we create the trie. And as usual, let's create a temporary node here, and we can iterate over the letters of the word and move the node to the child corresponding to that letter. And today I'm going to use convert the word into the char array and iterate over the characters. So if you remember, we need to check, and here I need to I can do this because we assume that all the characters are lowercase letters, and this expression would move my index to the if it is A to the 0, if it is B to 1, and if it is Z to the 25th or something. And I need to check if it is null initially. If it is null, I need to initialize it. Otherwise, I move my node to that node. So as you can see, I have in many places this expression. What I can do is I can assign it to the dx, something like this, and use here dx. Okay, and here also. Okay, and if we are at the end of the loop, we know that we are at the last node, so we need to set this attribute to true. Okay, now we have a function which we can insert the words into the trie. I'm going to adapt a little bit here. I'm going to add a final here because we are not changing the parameter word at all. And let's implement a search method. So very similar to the insert, we can just move our iterate over the letters of the word and move our node to the last one, move our node depending on the characters, and once we are at the end of the letter, we would have a node which corresponds to the last letter, and we can just check if it has a Boolean flag here. That would indicate that the word indeed was inserted before. And I can just copy this here and just return if this flag is set. So that should be it, but I don't I cannot just directly copy it here. This is wrong, because if it is null already, I can just return false, because that means we don't have any character at this point, which we don't have any node which corresponds to the character at this point in the word. So that, which means there's no any subset of the tree which we can explore and go. So, which means the word wasn't inserted before. Okay, that is it. And then similarly, we can again copy this method and This is correct, that if we add this, if there is no character corresponding to the node, to any node which we can move, that means the word wasn't inserted before, then we can just return false. Then we move to that child, and here we can just return true. Because this is this checks the checks if the prefix exists in the trie, and if we finish the loop here, we can just return true, because it means indeed there was a path from root to some node which we can follow using the prefix. So there must be a word which was inserted before, and we can continue to that if we want to. So the prefix exists. And I think that, so this is wrong, this should be prefix. Do I have any other error? I think that is it. I can test this. So yeah, let's just test with this. Okay, for that I can submit, and the test passed, but this is not updated. Let me check it again. Oh, I indeed submitted it, I think. So let's just submit. Okay, so as you can see, it passed all the tests. And yeah, this was a standard trie implementation. Now we can move to the next. So this X here indicates that it was solved. So the next one was this one, 211. Design, add and search words data structure. Let's read the description. Okay, so we need to add, we should be able to add the words into the data structure, and another method which, okay, this is exactly similar to my previous video where I explained how to find patterns within trie data structure. Here we don't find all the matching words, but we just check if there is a word which can match the pattern. And here are some examples. We create a dictionary, we add words, and we search on a given pattern. So there is no match for it. There is a match, there is also a match, and there is also a match for this bad. Again, all the lowercase English letters, only a dot as a single wildcard pattern. Okay, so let's quickly implement this one also. One thing which is different from my previous video explanation is here we are not looking for the words which can match the pattern, but only check if there is at least one word which can match the pattern. So let's quickly add the trie node. And again, I'm going to use isEnd. And now I'm going to, instead of creating an array of size 26, I'm going to use hashmap to store the child nodes of a trie node. For that, I'm going to have a character and a node. Let's call it children. Let's initialize them. This is a children new hashmap. Okay. These errors are okay because if I understand correctly, the Leetcode itself is going to import the util library, so I don't have to import it, otherwise it will be an error. And let's first also create our root node. And let's initialize it when we create the dictionary. Okay, now we can implement the add word method as usual. Let's have a temporary node, and again let's go over the characters of a word, and I'm going to use 2 character array method. And here now we don't have index, but we have a hash map, so we can directly we can do this. If absent and let's move a node okay, so I'm going to set is end to true at the end of the loop. Here we have a node children, which is a hash map, and if I don't have so instead of this I can do this also to make it more clear. Contains key, if I'm not wrong. Instead of it, if it doesn't contain a key, I can put a new node here. This is basically as before. If we don't have a node which wasn't already initialized for the given character, we just initialize it. So this does the same thing as we did with the array of children as an array. So here I use a hash map, but for now let me also resolve the but I can remove this and just use this one here. Okay, that is it for the adding word to the dictionary, and again I am going to change this a little and change this to the pattern. So we are searching a pattern inside the dictionary, and for that again I'm going to use a helper method, and let's call it search helper, which is going to get the root initially and the pattern position inside the pattern. And that's it, because we don't have to store the prefix or the result set, because we are not looking for the word. We just need to check if it exists that can match the pattern. So this looks okay, and I'm going to implement it as a that returns boolean. If this search returns boolean, then we can return true. Otherwise we return false. Let's implement this helper method. It's going to be boolean search helper. I'm going to call it no node final string pattern, a position within the pattern, and this is going to be a recursive function. We are going to add here a terminating condition. So if this node is already null, we can just return false. And similarly, we can check if the position at the end of the pattern. In that case, we can, for now, I'm going to return, let's do this. If we are here, we know that we can check that we are at the last letter. So if this node is has a flag which is true, or let's just do this, return. So if it was set to true, we know that we can match this word. If it was false, we can just return that there is no match, which is false. And again, let's get the character at position. And if it is dot, then we are going to do something, otherwise we are going to just move to the next node. So here we are going to iterate over our alphabet, and it was all lowercase English letters. And so I'm going to continue the search like this. If it returns, we can here return also true, because we know that we found at least one word which is okay. So we don't have to continue with the so for example, we have a dot character, we continue with the child which is starts with the A, then we can go to that child node, and we know that it didn't find anything, so this function returned false. Then we go to the next substitute character, which is B, and if we find something, we just return true, because we don't have to continue with the C, D, and other characters, because we know that we already found one match when substituting dot with the B character. So here we are going to just we can do get and see, and the position should be increased by 1. And similarly, here we can directly go to the next node. I think we don't have to, so we can do this. And char at position, pattern, position increased by 1. So if we have a dot character, we are trying to substitute it with all available letters in our alphabet. And if you find anything with any child corresponding to the letter in alphabet, we can return early. And then if I have a specific character, I can just continue with that child, and if it returns false, which is which means there is no match, it's okay. We are also going to return false. And if it is returns true, which means there was a match, that is also okay. Anyway, I am going to put it into else. Now thinking about it, I think I like this more. Okay, I think that is it, and let's try to test this. Okay, with the default test case, there was an error. Oh, I assigned. Not here. We cannot update final variable. So let's test again. Quit. Test. Okay. I need to get the note from the children. Have it here. Yeah, I should have looked into the errors. Now everything looks okay. Let's test again. .44. Okay, let's do this then. It expects a return value. Okay, seems to be alright. So the actual and expected are the same. Can I change the test case? Okay, I need to close this, I think. So here I can add some more, I think. So let's add all dots. Okay, I did something wrong. It should be all dots and here search. Right, so advert, then 5 search, yeah, looks all right. Okay, it also matches expected true, and let's submit it. Okay, this also passed all the test cases, and the last problem was, so I can refresh this. The last problem was word search 2. Does it? Yeah, 212. Let's open it. Okay, now here we are given a board which consists of characters and a list of words, and we need to return all the words we can find inside this board. I think it's better if we open it from the web browser, because you can see the examples. Can I see the examples here? So here is the first example. So we have a board and we have some words we need to check if we find inside this board. And here, as you can see, we can find it and os. And in this one, we cannot find anything. Okay, I think it is also possible to solve this problem without using trie. We can just recursively search and try to match any given word inside the board. And as you can see here, the limits are not so high, which indicates it might be a recursive solution might be enough here. So maybe I first try to solve this using recursion. Then we can try to add a trie data structure and how we can use it to find the words. Okay, let's do this. So what I'm going to do, can I assume all the words are lowercase English letters. All strings are unique. And the board is never empty. Okay, let's do this. For each word, I am going to search it recursively inside the board, and if I can find it, I can add it to my result. So I'm going to use again helper method. Let's call it find in board, and it's going to get a board and a word. And if this returns true, I can add it to my result. And I need to return result. Okay. Inside the helper method, we are going to look for each character in a board, and if the first if that character is the same as the first letter of the given word we are now searching, then I can start my search from that position, and I can move with each recursive call to 4 directions, right? I can move to given a position inside the board, I can move up, right, left, and down, and continue my search from there. Okay, I think I can do that. Let me implement the methods. First, I'm going to implement find in board, and that is going to return a boolean, and it gets a board and a word. And if you remember, I told that I can check for each character inside the board and try to see if it is same as the first letter of the word I have in this method. So let's do that. It's always better to use row and column for that, and I'm going to use that. So board length is going to be my row. I have a problem here. More than that, and column is going to be and here if I can check if word character at row column equals to character at the first position, then I can start my search for the word from this position. And for that, again, I am going to use another helper method. So that is going to be, let's call it search. I don't have any other method named that. So it's going to get a board, word, the position inside the board, and that's it. But this is going to return true or false, and I can do, if this returns true, then I can directly return a true, because we find inside the board that can match the given word. Otherwise, return false. Okay, let's implement that search method. It's going to get the word, string word, and row and column. And in this kind of problems, I need to first check if I'm within the boundaries of the board. So I'm going to check if row is below 0 or row equal to board length, or column below 0 or column equal to and I can return directly false here. And again, so what can be other conditions so that we can terminate the function early? And I can also check one other thing I wanna get is also the position, and this is going to be 0 initially. I can also check here if the current character inside the board is not equal to character at position, then I can return false. Okay, now we know that we match this character with the letter inside the word at index at the given position, and now I can expand my search to my 4 neighboring directions. So for that I can do I'm going to do something like this, a direction, and create a directions array, and that's going to be next row and here if I can directly call if search starting from the neighbors So word position increased by 1, and next row and next column. Then I can return here true. Otherwise, if I am here, I can return false, which means I couldn't find any matching word. But there are some problems here. We need to. So with recursion, when you start with within some position and you continue with the next one and the next one, you may come back to your same position. So you need to flag the position you already explored, so that you don't come back to this position again. Otherwise, it will be a cycle, and you wouldn't finish your search at all. And for that, we can do what we can do is we can directly update our board. Here I need to okay, let's call it a visited marker. And once I am outside of the word, I need to put it back to the position. Okay, but I need to do that also before returning. So otherwise, if we, for example, we put markers to the position we already visited and we continue, and if we are here, we find a match, we should put back the original character which was inside the board back, so that we leave the board intact once we finish the recursive function. Okay, but to do that I need to remove the final from the board. And let's add this private final char visited marker. Let's put it hashtag. And I am also going to let's call it final. So here I can put static teacher direction. So basically I can move down one and move up one, and move to the left and move to the right. Okay. One other thing is when do we return true from this method? So that would be if we are outside of the position word length. So that means we explored all the characters, and we could find a sequence of characters in the board, and we are at the last position. I should do that. Okay, this is a little bit tricky now. Here I'm going to return true. Now I'm not sure whether this one should come before this or after this one. This looks alright to me. So we are at the past letter at some point, and we move into that, and if we so maybe I should check that before going into the, yeah, let's do this. I think it's better if we do this, next row and next column are equal to character at position. And I don't have to check this, and we are here, we can just return. This condition is very similar to how we enter into the a function itself, right? So and okay, everything looks all right to me. There are some problems here, and these are about the imports. Let's test this. Let's use the default ones. Index out of bounds, where's that? 40. All right. Let's do this. Let's create a helper method. Let's call it on boundary, and we are going to get the part. Of column, and check this. Not on boundary, turn false. Similarly here, what we can do is if not on boundary, but with the next row and next column, or board next row is not equal to position +1, and we can just continue. And I don't need this condition here. Okay, let's test again. Again, we have some out of bounds errors. Why I arrived to this position. Something's not right. I'm at some position. I check this here if I am already at the end or over the word list. Can I see the test case? If not on boundary. I think this is okay, let me see. Let's start from the beginning. So we start from the this position and position 0 on some row and column. We check if we are on boundary. So if not on boundary, then return false. And if I am outside of the length of the word, return true, which means I consumed all the letters. What about this one? So I am here. I think this should solve the problem. Basically, we are considering when we enter into the search function next letter, because we. So looks all right. Let me also submit this. Okay, all tests pass. So as you can see, we didn't use, so I can make this bigger. As you can see, I didn't use any try at all to solve this problem. It was just pure recursive function. So given a current letter, which is same as the first one on the board, I try to continue my search looking into the neighbors up, down, right, or below, and so on. But maybe we can improve this a little bit by using try. And so the idea would be, as you can see here, we are checking if my next cell inside the board, either one of my neighbors, if not equal to the word, to the character at some word, I can just stop there. Instead of doing this for each of the words, I can do that for all of them. Right? So the idea was here, instead of looking for all the words inside the board, I can do that find in board, but just get the trie root. So that means I can start my search with let me think. So I can here use trie root as an input to my function, and check here if any children available which match this character at some cell of the board, and if it is, just continue the search from there. And yeah, I think that's the idea. So let's try to implement it. The very first thing is I'm going to again since we need to return the words also, I need to, okay, let's do this. Public static class node. Here I am going to use, we can use isEnd here just as a flag to indicate that the word is available inside the trie. But what we can do is also store the word itself. I think that's going to help us because we don't have to construct, we don't have to use prefix array, list of characters, and construct a string when we find a match. We can just use the word which was stored at the last node of the trie. Okay, I'm going to use array as a children, and let's initialize as usual. Let's put null initially here, and this is going to be new node of 26. Or let's just use 128. I think it's much better. Okay, then I need a root. And let's also add we need to add so let's implement private void words. Not this one. And if I need to initialize it. And move my node here and there. And here, instead of setting a flag, I can just what did I call it? Word. Assign it to this word. Right? I call it word. Okay. Then let's add our words here. Let's change it to and we add the words into the trie, and I need to change my function find in board. So we are getting the board, we are getting the root. Oh, what can I? No, okay, I can get the root from the class itself, but I think I need the result because I should add the words I find into the result list. Okay, now here what we can do is if this condition holds, so that means there is at least one child which starts with this character inside our trie, then we can start our search from there. Right, and I think I need also a result here. And this this can be void now. Okay, all looks okay. Now what do I have? So I start my search from this position, the node, and I also get the result list. Everything here I need to check if I am outside of the boundary, and then return. I don't return false, but just return. Should be void. And here I also, if this is outside, I need to add to the result the node word and return. So I know that I matched at this point some word, and that is stored at the current node, and I can take the word from it. I am not sure if we need to have this position +1 here. Maybe we see. So now everything is as before, but here we check. The problem is maybe not. So okay, now it is a little bit clear. Here I check the if root have any child nodes which starts with this character, but as a node to as a parameter to this function, I put root itself, but not the child which has that character. So here we don't have to add 1. If I'm at this position, what do I have here? Okay, let's do, I think it's more clear if I do this. Okay, let's do this. Okay, then I also need to, okay, yeah. If there is a child node which has, I can put that node itself. So that means I match the first letter with that node. Okay, now this looks okay. And here again, I need to change this to Okay, it should be null and children. If it is null, which means there is no child corresponding to that character, then I can skip this cell. Otherwise, I want to, so I have word position, row, column, the note itself. So note will be it's a little bit convenient to repeat it, but let's just put it there. Okay, then the result. And it is not Boolean now, so I can skip this. What about this one? Okay, this looks okay. Yeah, so I continue with the search, one of 4 directions, and of course I don't return any Boolean value. Here, okay, we don't have a word, right? So we have and I don't need also position then. Okay, I also don't need the position, but what do I need to check here? Okay, another thing is if note is null, I need to return. But here, do I have to check if... So I think if I know that word is not null, then I can add it to my result. But I don't return. So yeah, I think that looks okay, because the idea is I'm searching through the board, so I am at so let's take the example from the problem. So the idea is, for example, I start from EAT, I find this word, and if it is, it means we are at the node which has this word in its attribute as a field, and then I add this to my result, but there might be another word. For example, here, if it was S, it also makes another word, so I don't return if I have this condition here. So this one is, for that I need to save. So here let's do let's call it char position, even though it is, we don't have a position. I need to save that, and then I need to assign it back to the board. Okay, here also we don't need this one and this one. So let's okay, only the imports. Let's test this one, the default. Wrong answer. Okay, I don't return anything. let's check why. It should be when it is equal to null, not equal to. That was the issue. Okay, let's do the test again. I think I have mapping for that. Okay, now we have actual and expected answers. Okay, let's. I'm not sure if I can make another test. Let's add some one character words. So for example, I want to add et a f. What is not? Oh, I have a typo there. So it should be string. Okay, we don't. So we have here a, and we can find in many places. So my answer, is it written in the description? It should be only unique. I think I remember something with the unique. What does this mean? Is it all the input words are unique, or? Okay, let's also add this one. Oh, who was it? Okay. So, and okay, second one also as expected, but so when I find a word, we can just set it again to null. Let's test this. Okay, this looks good. So I didn't get this from the problem description, but apparently we need to return all the unique words. One other thing was maybe you can also here, just before returning, add it to the set and again convert it to the string so that it will be returned. But let's submit this. Okay, all tests passed. So one last thing I want to do before finishing this stream. We can do some complexity analysis. Here for this method is the adding number of adding words to try is dominated by the length of each word. So the time complexity would be O of max length of a word. That means you are given a list of words. The time complexity of adding words into a trie is of the maximum length of the word in the list, because we have only one loop here, as you can see, and the space complexity is we can make it of 1, because we don't create any other memory location, only the required ones, and that is for the each node here. But I don't think that is usually added as extra space that we use for the function. And then maybe we can first we don't have that methods anymore. We can try to analyze the recursive one, the previous implementation we did, and for that, if you remember, we took each word and tried to find it on the board. And the idea is we have 4 different neighbors, and for each character we can start our search from those 4 different locations. So idea would be for the first character I have 4 options to look for to start my search again. For the next character, another 4 ways I can continue my search, and so on. So the idea here is it will be dominated by 4 over length of word, because for each given character you can continue your search in 4 different directions, and once you reach to some termination condition, you recurse back and continue with the next one, and then recurse back and continue with the next one. So this is upper bound, but it is not exactly upper bound. It's slightly lower than this, because for the first character we already start matching. So we have length minus 1, but in general we can take it, time complexity would be 4 over maximum, again maximum length of the word, because that will be the dominating one. And the space, for space complexity, for each word we start a new recursive call, and that is also considered as a space because we allocate space in the stack. So for each call allocates some memory in stack, if you know that terminology. So we can say tell again length of word. Again, this I assume here the maximum length of word from the list of words. So that is time for recursive solution. And with the trie, let's see. So I think we don't. So for this function, find in board, we nothing changes. We still need to search for the for each letter inside the word, and only thing that changes in the find words function here, we don't have another loop iterating over the words instead we have only find in board, so we just removed one loop from the function using the try. I hope that is clear, and maybe I can we can do this. So the first recursive solution was number of words multiplied by 4 over max length word, and with trie data structure we just remove the it is 4 over max length of word, and the space complexity is the same of max length, because we have the recursive function. So I hope that is clear, and we also discussed the trie complexity when adding the words, and what was the other? So let's also look into the we can also check. So it's adding words is the same for the insert here for the trie data structure, and this search is also same. It is of length of the maximum word, and also prefix here is length of maximum prefix basically. So that's it for today. We solved 3 problems from Leetcode, all related to the trie, and this one was a little bit hard, but you can still solve this using recursion and also using trie. And I believe if I update this, maybe we can see the difference in the running time. Submissions. Okay, which one is? So recursive one was much faster than the trie one. Okay, I don't know what's going on here, but maybe that's the case. I'm not sure. So I'm going to check it, but maybe it doesn't really indicate the running time. So that's it for today. Thanks for watching, and bye.